Let us see about asynchronous clocks. From the previous examples, it is clear that setup and hold checks for multi-frequency clocks can become complicated. So here multi-frequency clocks can be either slow fast or fast slow, which will be having different frequencies. And coming to the definitions of setup and hold, we already see in this one. So setup is something like the minimum time for which data should be maintained constant before the arrival of clock edge, whereas hold is something the minimum time for which data should be maintained constant after the arrival of clock edge. The complexity increases drastically when clocks are asynchronous. So asynchronous means they won't share any fixed phase relationship, or they may be coming from two different clock sources. That is, they do not share a deterministic phase relationship. Next, coming to key characteristics. For asynchronous clocks, the relative arrival time of launch and capture edges is non-deterministic. This means the setup and hold requirements could vary from cycle to cycle. At some point, an edge pair will have very little margin, and since static timing analysis always considers the most restrictive pair, such crossings will always result in violations if treated as synchronous. Next, coming to the problems. Generally, the problem that we face is metastability. So let us understand what is meant by metastability. So in figure 7.1, two domains C1 and C2. So this is a figure which is having two flip-flops F1 and F2. One is driven by C1, another one is driven by C2, and there exists a common data path from C1 to C2. If the input of capture flop F2 changes very close to its active edge, the captured value may be unstable for a period of time. So we need to give some sufficient amount of time for the data to get captured at the capture flop F2. So before that, if you are launching any data from the flip-flop F1, this may lead to the corruption of data. So we are not sure like the data that is received at the capture flop is right or wrong. Means it can be either 0 or 1. So that goes into the state called as metastability. So this unstable condition is called as metastability. So metastability does not mean functional failure, but the output of F2 may take an unpredictable time to settle to a valid 0 or 1. So this capture flop is not sure whether it is 0 or 1. So it is called as metastable. To handle this, synchronizers, example, two flop synchronizer chains are used to bring signals safely across asynchronous clock domain. So in order to overcome this metastability problem, generally between F1 and F2 we place two flop synchronizers. Next, coming to main problems with asynchronous clock domain crossing. Each edge pair has a different timing requirements. Since the tool must always check the most restrictive edge pair, there will always exist a violating edge pair. Hence, if left unhandled, asynchronous crossings will flood STA with false violations. Next, coming to the solution. To prevent implementation or STA tools from wasting efforts on such asynchronous parts, identify asynchronous clock groups explicitly. So this is done using the constraint. So the constraint that we need to set is set clock groups hyphen asynchronous hyphen group C1 and hyphen group C2, meaning that C1 and C2 are asynchronous. So here if you can see this particular figure, F1 is driven by C1 and F2 is driven by C2, and there exists a common data path from C1 to C2. So if data comes fast from F1, because of which this F2 cannot capture it, means we are not giving some sufficient amount of time for the data to get captured at F2, it enters into a state called as metastability. So in order to overcome, in between this F1 and F2 we place two flop synchronizer. So before that we need to declare a constraint by saying these clocks C1 and C2 are asynchronous. So this tells the tool not to attempt timing checks between these domains, ensuring that only functional synchronizer structures are considered instead of impossible timing requirements. So this is all about asynchronous clocks.